Hello, my name is Evan Laljit and my research is on the effect of cold temperatures on the dynamic response of marine composites. Composite panels are structures composed of various layers of metals, fiber-based materials, plastics, etc. sandwiched together. Since they are easy to manufacture, have a low cost, and have a high strength-to-weight ratio, they are commonly used for constructed marine vehicles used for various different companies/organizations for different uses. Some vital examples include military use, detecting and mapping the ocean, and researching different phenomena related to the ocean, such as underwater volcanoes, ecosystems, cave systems, and more. As such, understanding the effect of water-based impacts on these panels, specifically in freezing temperatures, is essential to the design of these marine vessels operating in extreme temperature conditions. So far, previous studies have researched the structural deformation of these panels as well as point-wise measurements of the fluid domain. However, we seek to further research this phenomenon by measuring both the structural and fluid dynamics for the entire field, providing further insight in the fluid-structure interactions. As shown, the experiment is done using a gas-driven cylinder to drive a spherical object into a tank of water, where a circular composite panel is placed below. Techniques based on digital image correlation, otherwise known as DIC, and particle image velocimetry, PIV, are then used to measure the panel movement as well as the fluid movement, respectively, using two high-speed cameras. In our experiment, we used DIC to track the in-plane movement of the plate using speckles, as shown. Then we use an open-source software named NCore to construct the out-of-plane displacement throughout time and along the full field of the plate. Then, PIV is utilized to track the movement of the particles placed in the fluid between each consecutive image taken. The velocity field of the fluid is then constructed from these images using MATLAB software. A pressure sensor and the Navier-Stokes equations, which utilizes the velocity and other parameters, are used to obtain the pressure field. These measurements are taken at 24 degrees Celsius and 5 degrees Celsius, with 5 trials each. In addition to the PIV and DIC techniques, an image segmentation model is built upon and employed to aid in automating the PIV analysis process. Now let's take a look at some of the results. The plot shown on the left displays the movement of the center of the plate versus time for room and cold temperatures labeled RT and CT. The solid lines are the averages of the 5 trials, and the shaded regions are the standard deviations or uncertainties. The plot on the right shows where the maximum and minimum deflections occur for room and cold temperatures. As you can see from both plots, the difference is not extremely high. We can also take a look at the side view deflection of the plate for different time instances. These times run from the first upward to the first downward movement of the plate. Again, there is not much of a huge difference here. Here we analyze the velocity field as the spherical extruder enters the water tank. The bottom and top white portions are the plate and extruder respectively, and the colored regions is the fluid. A scale is provided on the right. The first video is for the room temperature measurements, and the second is for the cold temperature. Once again, we see no significant difference. Unfortunately, because it was determined that the pressure sensor did not record the data properly, we cannot showcase the pressure field plots since they are constructed from this data. However, from the plots of the plate displacement and velocity fields, we can conclude that the behavior of the structural and fluid dynamics in room and cold temperatures show no significant statistical difference. This result is incredibly impactful as it reveals new data previously neglected, and it opens up a brand new path in this research sector regarding the behavior of composite materials undergoing hydrodynamic loading in cold temperatures.